the quiz problem for you to prove it. Now, I would like to describe a related concept called inclusion-exclusion inequality. Okay, so that is based on the inclusion-exclusion identity. Okay. All right, so indeed it is a set of inequalities. Now I state the simplest one. Right, so the probability of the union of a finite number of events E sub I can be upper bounded by the summation of the probability of individual events. And we call it as Bool's inequality. So we give a special name for this simple inequality. Okay. So remember, if we want to have an exact identity as described in the inclusion and exclusion identity, we know that is equal to actually a sum of several sums. Okay, so maybe I recall the sorry. So that so indeed we can express the probability of this union, right, by a sum. Okay. So we used a dummy variable R. Okay. And R from 1 to n. Okay, so some summation of the following terms, and each terms is related by this power of mass 1, and also we need R indices. So we know we have I1, I2 up to I sub R. Okay, and with this order, and they are all in between 1 and the n. All right, so this is summations for the probability of the intersections of E sub I1, E sub I2 up to E sub IR. Okay, so this is the exact expression. Okay. And as we know, it's actually can be write down. So this is a sum. So we add this summation and then subtract the following summation about the intersection of two events, okay, indexed by I1 and I2, and specifically ask that I1 is less than I2, okay. And then we add a term here, okay. Okay, this is probability of EI1 intersect EI2 intersect EI3. All right. So now, we actually we add and the subtract, add and subtract, etc. alternatively, and so this will be okay. Okay. I do not have enough terms, enough space, so I will use the space here. All right, and the last term would be the intersection of all events involving in the union there. Okay. So this expression, this is the reason why we say inclusion, exclusion, because for the sum we say that this is the term for inclusion. And for this is sum, because we subtract this sum, so this is for the exclusion. So inclusion, exclusion, inclusion, exclusion. All right, so that's the name I have explained the last Thursday. But now, suppose that we want to use this sum only, the first sum only, and because we do not do the exclusion, means that we do not subtract this sum. So that this sum would be too big. Okay, would it be too big? And so that this would be upper bound. But what happens if we decide to do the subtraction? So we will do the exclusion here. And it turns out that when we do the exclusion, sorry, right? Then it turns out we will subtract too much, so then this becomes to a lower bound. Okay, this becomes to a lower bound, and what happens if we include the third summation here. Now we decide to include right? So if we include the third term, then this becomes too big, so it becomes to an upper bound again. Okay, so you can see we were alternating in the direction of the inequality when we include more and more summation. But of course we were abiding to the inclusion exclusion formulation here. Okay, so you see here. And so what is the general formula for these inequalities? So let me write it down. Okay. Okay, so in general, we have, okay, and remember, actually, if the last term is an inclusion, means the addition, then the inequality will be here, like this one. So this becomes to upper bound. But if the last term is about exclusion, means the subtraction, then the the result here in the right-hand side becomes a lower bound. Okay, so now it is, well, we will find that this probability will be upper bounded by if we have here and plus 1, right? Because this is the general formula we have. And you see the last term is the R. R is an odd number, and an odd number plus 1 is an even number. So when this is even, then this is a positive 1. All right, so the last term is about inclusion. And because this is inclusion, so this is come to an upper bound. Okay? And the lower bound is corresponding to that the R is at up to an even number to K. Okay. And of course, right, the biggest number in the summation, either 2k minus 1 or 2k, should be less than n. Okay, why? Because it's reached to n, then you will have the identity already there. Okay, so whenever the sum is not a complete sum like in this identity, then you will get inequality there. Okay, so that's the general expression you have. Okay. And the proof is a little bit tedious, and so I think it's about 1 page. And so, the key idea has been presented in the textbook. So, okay, and I believe you already studied it in the preparation of quiz number 2. Okay, but if you still have question about the proof given in the textbook, let me know. Maybe I will send you my proof. Okay. Okay. Any questions? Right. Good. Okay. All right, I will talk about discrete sample space. Which means that we will, when we consider running experiments such that when we establish a mathematical model, and then we find out that the set of all possible outcomes is discrete type. All right, which means that it is a countable set. Okay. All right, a special case for, okay, so let me see. In many random experiments, especially, quite a few random experiments ask you to do in the recommended exercise number 2. Okay. So, what's the sample space? right? Okay. Right, so it's natural, we know, to assume that maybe I would say it is quite often to assume that all outcomes in the sample space, okay, are equally probable or equally likely to occur. Okay. Right, and in this case, the sigma algebra we select would be the power set of the sample space, and the probability function okay, or the probability assignment becomes right here for every event in the sigma algebra E. The probability would be the ratio of the size of the event and the size of the sample space. All right, so in the end of this section, then we will justify that this assignment established. Okay, so establishes a probability function F. Okay, and this probability function will give a special name, which will be called accounting probability function. Okay, so counting probability function will be considered when the random experiments is fair. Okay, fair. I have mentioned fairness in quite a few random games. Okay, right. So one of the purpose of this section is actually to prove. Of course, we will prove more than we need in this section. Okay. Any questions? Okay. Right, so we will consider a sigma algebra F on a sample space. All right, so the sample space is general, so it's not necessarily countable. Maybe it's uncountable like the the running experiments that we want to measure the lifetime of a light bulb manufactured in a factory. Okay, so and the sigma algebra can be arbitrary. Okay, can be arbitrary. Now, an event G in the sigma algebra F is called atomic. Okay, if it is a minimum non-empty event in F. All right. Namely, if H is a non-empty event in F, and we know that H is a subset of G, then H must be equal to G. Okay. So, which means that it's impossible that we have a non-empty event H, which is a proper subset of G. It's impossible. Okay? It's impossible because it's a minimal non-empty event. So any minimal non-empty event is called an atomic event. Let me check an example. All right, so consider some running experiment with sample space, which can be denoted as a set of 1, 2, 3, 4, 5. Okay. All right, and the sigma algebra selected will be right, which consists of 4 members only. And you can check that it's indeed a sigma algebra, all right, satisfying the 3 properties required we mentioned before. Okay. So it's a sigma algebra. So this is a sigma algebra on S here. All right, and here we can see they are exactly 2 atomic events in the F. All right, so which are what are atomic events here? Well, this member is an atomic event, right? Because that no other member which is not empty and is a proper subset of this member. And so 1, 2, and 3, 4, 5. Okay. Yes?
The elements in the sigma algebra should be 2 to the power 5, right? Number of elements.
You mean in F?
Yes.
Yeah. Okay. Every members in F is a subset of the sample space.
Yes.
Yes. So.
In the example, the sigma algebra.
Yeah.
It should be 2 to the power 5 elements.
Not necessarily. 2 to the x, the power set of x is just one of the possible sigma algebra selected. This is still the simplest sigma algebra would be this one, right? This is the simplest sigma algebra. For any sample space, this is the simplest because it has S, right? As a total event. And because X total is there, so all the complement should be there, right? So the complement of the total event is the null event. Yeah, so these two should be in any sigma algebra. All right, and the collection consisting of these two members already is a sigma algebra.
Because these two elements satisfy the
The three, yeah, the countable activity, the countable union, yes. Yeah. So so I select this one. Okay, it's a sigma algebra, and we find these two are atomic events. Now comes with the example you asked for. Okay, if X is a countable set, okay, and we set the sigma algebra to be the power set of X. Okay, so this is quite often to occur in many practical random experiments. Okay, so you will select this one. Then atomic events in F are just singletons. Okay. For outcome, or any outcome in the sum space. Right. So this is the example you asked for, right? Yeah, we can select. Okay, when X is a countable set, then we quite often we select the sigma algebra to be the power set of the countable sum space here, and in that case, atomic events are just singletons. Okay, because every atomic event, every singleton is an event of in the sigma algebra, okay. And they are the smallest one. Okay, because they each of them consists only one element. Okay, so this example, I think most cases we consider this, but sometimes we may consider sigma algebra like this one in very special situation. In very special situation.
So
yes?
Two properties for atomic
Events.
atomic events,
Yeah.
which is what are those two properties?
Oh, well, atomic events by definition is here. If we can find, suppose we can find a non-empty event in F, and this event is a subset of G, then they must be equal.
What is set G?
But I'm sorry.
What is the set G?
The same.
The G set.
G. Oh, we say G is an atomic event. Right. Just like we say this is an atomic event. How do we know that? Well, we search for events in F, okay, which is a proper but non-empty subset of this event. But we can't find anyone, right? So it is minimum. But the total event is not the minimum, right? Why? We find at least the two, right? Non-empty event, which is the proper subset of X. So X is not atomic. Mm-hmm.
They have to be a subset and then they have to be equal. Then
Okay, this is the description, right? If and then, okay, and logically to say another description would be All right, another says that if there is no non-empty event, H in F such that okay. So G is called an atomic event whenever there is no non-empty events H in F such that H is a proper subset of G. Why? Because if we can find an event in F which is a proper subset of G, then H is smaller, right? A smaller event than H and then G. Okay, so that G is not minimum one. Okay. All right. So this is to define so-called the minimum element in a set. All right. In this collection, the minimum one. Okay. And there are many different minimum events. Okay. Okay. Other questions? All right. So now the concept from the concept of minimum event, atomic events, then we will deduce a few propositions. The first one says that atomic events in F are disjoint from each other, namely if G1 and G2 are atomic events, in F, then the intersection of G1 and G2 should be equal to the empty set. Okay, so atomic events should be disjoint from each other. All right, so we prove this by contradiction. So suppose that they are two distinct I forgot distinct. Sorry about that. G1 and G2 should be distinct. Because if they are the same, of course the intersection will be themselves, right? So they should be distinct. Yeah. So suppose they are two distinct atomic events, G1 and G2, such that their intersection is non-empty. Okay, suppose that. Now, since G1 intersect G2 is a non-empty event in F, and G1 intersect G2 is a subset of G1. So we have all right, and G1 intersect G2, G2 there, okay? So we have that G1 intersect G2, so this is G1, okay? By the minimality of atomic event, right? So that, and this is G2. So now G1 equal to G2, and this is a contradiction. Why? Because G1 and G2 are distinct events. Okay. So that's G1 intersect G2 must be the empty set. Okay. So this is a very simple proof by contradiction. Okay, so G1 is here. Suppose G1, G2. So these two are distinct atomic events. And suppose they have a non-empty intersection here. Because for two atomic events, there are only two cases, right? Either this case, right? They are disjoint, or they have non-empty intersection. Only there are two possibilities. Okay? And then I will eliminate this possibility. But assume that this is true. Okay? When this is true, and this intersection is not empty. Okay? So this, and because F is a sigma algebra, so the intersection should be also in F, right? We can do the countable intersection and countable union, right? Or countable, anyway, countable mainly intersection, union, complement, right? Whenever you do it. Okay, so now G1, G2 in F. All right, so this one is non-empty, and it is a subset of G2 because G2 is minimum, so that G1 intersect G2 must be equal to G2 here, right? By minimality of G2, and the same because G1 is atomic, so that G1 intersect G2 should be equal to G1. Okay. And then we establish this identity here, and which says that G1 is equal to G2. But this is a contradiction because G1, G2 are distinct. Okay? They are distinct atomic events. Oh, sorry about that. Okay, so this is impossible. Right? So we show this is impossible. So the only possibility would be this situation. They are disjoint to each other. Yes, please.
How is the interaction equal to G1 in the last step?
This one?
Yes.
This is G1. All right. We know G1 intersect G2 is a subset of G1, right?
So G1 and G2 are, can you explain it by some example?
Again, the definition
From some example.
from the example here.
Like, can you take an example for G1 and G2?
Well, this is G1, this is G2. They are distinct. Okay? And apparently, they are disjoint, right? When you take an example, because this is always true, so you cannot find two atomic events, different atomic events, has non-empty intersection. You can't find it. Because this is the fact, a theorem. Okay? So whenever you take an example, you can't find counterexample. Yeah? Because that, right? So, but But you can't enumerate all possible examples, right? Because this must be true for any atomic events is in any sigma algebra. Okay, you cannot list all examples because there are infinitely many examples you can have. Okay, so that in mathematics, the technique to prove such kind of statement is to use proof by contradiction. Right. So and the starting point is to see there are only two possibilities. And when we eliminate one possibility, then the rest possibility will be true. Okay. Any other question? Great. This proposition is specific for finite subspace. Now, any non-empty event in a sigma algebra F on a finite subspace contains an atomic event. Yeah. So the situation is here. So this is our subspace, which is finite. So the proposition is specifically for the finite case. Okay. Right, and we take an arbitrary event here. Okay, in the sigma algebra F. Then this event will contain an atomic event. Okay, which is atomic in F. Okay. It's important to know it is atomic with respect to some specific sigma algebra. Why? You know, this member, right, is atomic in this F, right? But if the F is selected like this one, then this event is not atomic because it's not a singleton. Okay? So the same event, but if you consider different sigma algebras, okay, an event may be atomic or not atomic. Just like the richest person in Taiwan is not the richest person in the world, right? Correct? So because Taiwan is a small state and the world is the biggest state there. Okay. All right. So all right. So let E be a non-empty event in F. Oh, by the way, at least up to now, everything is about logical reasoning, right? Because we start the theory of probability from the scratch, right? So you should always remember this. Okay, we start from the scratches. And so all the argument or the deductions is based on logical reasoning. Okay, so it's some kind of challenging for your brain to think things clearly and deeply. This is the only requirement in the lecture room. But if you have anything which is confuse you, then you should raise your hands, okay, to clear the points. Okay. All right. So that we are non-empty events in F, just like. So I should say. Right, if E is atomic in F, then we have done. Why? Since E contain itself and the E already atomic, right? The statement says that every non-empty event contains an atomic event. Okay, so if E itself is an atomic event, then we have done. Then the proposition. But so the other case is if E is not atomic in F. Now, so E is not atomic. Not atomic, which means that there is one non-empty event, right? Such that this is true. Okay, none becomes some. You take the negative. Okay, the negative. So if E is not atomic in F, then there is a non-empty event we call E sub 1 in F, such that E1 is contained in E2 but not equal to E2. So E1 is a proper subset of E, I'm sorry. Okay. Now, if E1 is atomic in F, then we have done. Okay. Why? If E1 is atomic, then we know E contains an atomic event. That's what we want to prove. Okay. Otherwise, we repeat the above procedure and obtain a sequence of non-empty events E1, E2 up to En in F, such that such that En is a subset En minus 1 but not equal to En sub E1 and E. So if we do it, repeat it, which means that we find a subset. If it's not atomic, then we will find a subset, right? So again and again. So this is the procedure. Now since x finite, E is finite. Okay. So that the above procedure by the way, okay, they are all non-empty. Okay, so the empty set will be here. So that the above procedure must stop at n and n, which will be less than or equal to the size of E minus 1. Why? Okay, because every time when you find a proper subset, the size of this proper subset will be less than the size of E. Okay, so you reduce the number of outcomes in the events, and each time you will reduce at least one outcome. Okay, so that the longest chain, all right, for n would be less than equal to the size minus 1. Okay, which means that you cannot repeat the procedure indefinitely. Okay, it should stop at some time. Okay, and when you stop at n, which means that the En should be an atomic event. Right, so the stopping criteria is that you find an atomic subset, right? This is the idea of the procedure. It's a very simple procedure. Yeah. So you should stop at some n. Maybe I will say it's some n, which is less than or equal to E minus 1. And with E sub n, an atomic event in F. Okay. Because when En is not an atomic event, then it should contain a proper atomic event. Right? So you should be able to enlarge the length of the chain. Okay? But you can't do the procedure indefinitely, as we know that, because E is a subset. Okay, so finally, En is an atomic event and contained in E, right? So this is complete proof. Okay, this is complete proof. Okay. All right. I try to extend the theorem to countable set, which means that infinitely possible, right? Infinitely countable set, but not successful yet. But I can't find any counterexample, so there is no conclusion at this point. Okay. Okay. Right. But I will consider this question from time to time. So, okay, when I have time. But you can think about that if you are able to prove or disprove it. If I replace the finite to countable symbol space. Because countable set, there are two possibilities. Either it's a finite set or it is infinitely countable set, okay? like the set of all natural numbers. The set of natural numbers is a countable set, but it's an infinite set. Okay? Okay. But anyway, at least we have this case. So when the sum space, okay. So when the sum space is finite, okay, then and you can consider any sigma algebra, okay, because in any such sigma algebra, any non-empty event contains an atomic event. But when X is an infinitely countable set, and because we usually
Denote sigma algebra. That's how we usually denote the sigma algebra.
you mean F?
Yeah.
Yes, usually. Yeah, F always denotes an sigma algebra. Yes. So if we select the sigma algebra to be the power set of X, and we know the atomic events are all singular terms. So in that case, every non-empty event in F contains an atomic event. Okay, and that is good enough for us in practical situation, because in practical situation we usually select, when X is a countable set, we usually select sigma algebra to be the power set of the sum space. Okay, so in that case, then every non-empty event in here contains an atomic event. And we need that later on. All right, so a sum space, okay, is called discrete if X is a countable set. Right. And in probability theory, we usually use the word discrete sum space instead of countable sum space. Okay, it's just for historical reason. Yeah, but they are equivalent terms. Okay. Okay. The third proposition states that the collection, we name it as C, of all atomic events in a sigma algebra F on a discrete sum space okay, is countable. Okay. Why we need this proposition? Well, there is if X is infinitely countable, then if we select, then the power set is uncountable. Okay, it becomes to be uncountable there. So that it is possible that when the sum space is discrete, then the sigma algebra itself is an uncountable set. All right? But if we collect all atomic events in this uncountable collection, the proposition says that this collection is countable. Okay? Right. Now, by proposition 2.5.a, members in C are disjoint from each other since each member in C contains at least one outcome in S, in the sample space, and they are countably many outcomes in S okay, in the discrete sample space S. Okay, so the collection C is a countable set. Okay, so each member in the collection C contain one outcome because they are atomic events by definition are non-empty events. Okay, so that every members in C contain one outcomes, and because they are disjoint from each other, right? So they contain distinct outcomes. But we have only countably many outcomes in the discrete sample space. Okay, so that the collection of C should be countable. Okay. Okay, so let's take a short break up to 2:40. Right. So now I state the fourth proposition. So letter F. Let the square F be a sigma algebra on a discrete sample space such that every non-empty event in F contains an atomic event in F okay. So this is the premises, and then every event in F it's a countable union of atomic events. Okay. So this is the reason why we consider atomic events, because every event in F is a countable union of atomic events. So in that case, atomic event becomes to the building blocks of every event. Okay, so every event we can build up all possible events by atomic events. Okay, and these building blocks, okay, we have only countable the many building blocks as we described in these propositions here. Okay, in these propositions, when we discuss discrete sample space. But we need a constitution that every non-empty event in F contains an atomic event in it. Okay, so there are two possibilities, at least for our case. All right, so any sigma algebra, okay, in any single algebra on a finite sample space. Because this probably depends on the sigma algebra you select, right? But for a finite sample space, then any sigma algebra from proposition 2 point Y point B. Because in this proposition, we have shown that any sigma algebra on a finite sample space, right? And in that case, then any non-empty event contains an atomic event F, right? So in this case, it's okay. The second case is that F is equal to when X is an infinitely countable set. So if X is an infinitely countable subspace, okay, and we select sigma algebra to be the power set of X, then of course, for such a sigma algebra, then every non-empty event in F contains an atomic event. Why? Because as we have shown here, if we select the sigma algebra to be the power set of a discrete subspace, then atomic events in F are just the singletons. Okay, so the minimum event will be singletons. Okay, and both cases will be enough for our practical situations. Okay, so we consider this condition is not too restrictive. Okay? It will not hurt a lot, not hurt a lot about our applications. Right? Right, so we should prove, so the idea would be that in this condition, then every event is just, can be built by atomic events, which means that they just a union of atomic events. Okay. Right, so let's prove the statement. So we let C be G sub I. Okay, so let C be the collection of all atomic events in F where I is a countable index set. Okay, as shown in proposition 2.5.c. Okay, here. So we already proved that this collection C is countable. All right, so the index set is a countable set. Now, if E is the empty set, so if the event is the null event, then E is an empty union of atomic events in F. Okay? Empty union is still a countable union, right? It's empty. Okay. So this is a special case here. So now we let E be a non-empty event in F. Okay? And we let Jx an index set. Alright, so J is a set consisting of all indices in the index set I, such that Gi is a subset of E. Okay? Any questions about the definition of this? So of course this is, so the capital J is a subset of the index set I. Okay? So if the J consists of all indices such that G sub I, okay, is a subset of E. Okay, so you can think about that. So this is E, and we have said that G I is here, J something. Okay, So you may have like that. The etc. Maybe that. So we just collect all the indices here, such that when G sub I1 sub I is in G. Okay, and since I is countable, J is also countable. Okay, so J is also countable. Now suppose that we take the union of all G sub J such that the J is in the capital J. And of course the union must be a subset of E. But we suppose that it's not equal to E. Okay? And of course this is the joint union, so we can put that here. So suppose that this is another case. Then H defined to be E minus the union. Okay? And this one is non-empty events in F. Okay. And because it's a non-empty event in F, now by this property, any non-empty event in F contains an atomic event and contains an atomic event G in F. Yes, please.
What is that symbol between H and E?
Oh, okay. So so we check the union. This is event E, and we suppose here the situation is here. Okay. Okay, and so H is just this area. This area. Okay. So so this is H. Minus means that you delete all the elements in here. Yeah. So this is union. Oh, sorry.
So it's just H equals. So why there is a triangle?
Oh, sometimes we say it's the definition. Yeah, it's just equal. That's right.
So
Yeah.
H is defined.
Yeah, defined to be the difference state. Yeah.
Minus.
Yes. Yes. Yeah. Yeah. Some authors they like to eliminate it. Okay. But sometimes I like to put here. I say that this I define the symbol. Okay. All right, so now H is non-empty, okay, and because this is a non-empty event in F, so that it contains an atomic event, and this atomic event we will name it as G here, okay. So we now have atomic event G. Okay. Now, since RH is a subset of E. G is a subset of E. Oh, by the way, I should GI. Okay. For some GI, because I name all the atomic events as G sub I. Okay, so I should say atomic events in C. Okay. So for some I, maybe I specifically, all right, it's more specific. Okay, so this implies that I should in the J, and then GI must be a subset of the union. Okay, and which is a contradiction. So the contradiction comes from here. All right, so this is not be true. Thus, we have that the union equal to E. This is the only possible choice. I'm sorry. All right, so we have, okay, and we have done. Okay, so E is a countable union of the atomic event because the capital J is a countable set, as we just stated here. Right, so again, it's just a proof of by contradiction. Again. Any questions? Okay, and so I want to make an exercise. The total event X. Oh, okay. Please show that the total events is okay. Okay. So that's the special case is that the sample space should equal to the union of all atomic events. Okay, so now at this point, okay, under the condition here, we know that atomic events can, okay, be used as the building blocks of all events. Okay, so let F. Oh. FB. Okay, a sigma algebra on a discrete sample space X such that every non-empty event in F contains an atomic event in F. And let the collection C be the collection of all atomic events in F. Now, a non-negative valued function P on C. So C is just the collections of all atomic events with the summation okay, with the summation of all values, okay, of atomic events, okay, equal to 1. Okay, so any such non-negative value functions with this property can be extended uniquely to a probability function on F. Okay. So this proposition is useful, which gives you a way to construct a unique probability function on the sigma algebra F. Okay. The way is that, well, you can assign probability to each atomic event such that the summation of all the probabilities assigned to atomic events equal to 1. Okay, once you have done this, then you have established a unique probability functions. by extension. Okay. And the basic reason is from this proposition, because every event is a convolution union of atomic events. Okay, so before I give a proof, do you have any question about the statement here? Okay. Right, so the starting point here is that we have a non-negative valued function P. Okay, so the collection of all atomic events. So for every atomic event in this collection, the value will be non-negative. Okay, so that will be greater than or equal to 0, and the summation equal to 1. Okay, so this is starting point. So from this standpoint, we will construct a probability function as an extension of this function, and then we will prove that it is unique. Okay, so we will prove the existence and uniqueness of probability function on F. Now, by proposition 2.5.d, every event E in F is a union of atomic events in C. All right, so we let CE, okay, to be the collection of all G in C such that G subset of E. Okay, maybe I put triangle sign here as a definition. So define this collection. So of course that this is a subcollection of C. Right, and we know that the E is equal to okay. Right. Any questions? So atomic events inside the E, okay, becomes two building blocks. Okay, so they're just the union there. Okay, and now we define a real valued function we also call it P, okay? Or maybe I use F, a function F on F by F of E, I define it to be, so you know this is equal to okay, so the function is defined. So this is well defined because we know that from each event E, okay, we have the collection, okay, containing all the atomic events inside the event E, okay, so that we know E actually is equal to this joint union, right? Okay. And we use those atomic events inside E, all right, to give a summation here. Okay, so we have that. So this is the probability function. And we will show that F is indeed a probability function on F and is unique, and it is a unique extension of the probability function. Okay, right. So I will continue to finish the proof on Thursday. Any questions? What? If no, so I will see you on Thursday. Oh, by the way, we will have a supplemental lecture the coming Saturday, as I described in my syllabus. Okay, but you can watch the video from my YouTube channel, right? Okay.
Aren't missing any class next week?
I think this is for the spring break. Yeah, so we make up that for the future.